All right, so this is our second last lesson here today. We are continuing our unit on population dynamics by focusing on population growth. As we've discussed previously, it's important to be able to predict the future size of various populations of various species. And the best way to do this is by modeling their population growth. And by modeling their growth, we might be able to have an understanding of what population of species might either be under threat and then bring about the necessary measures to make sure that they don't go extinct and to bring their population back up. Or we might be able to find out, for example, that a population is growing out of control and might require us to take certain steps to bring that population back under control before it gets to the point where it starts to threaten other species in that environment. So in general, using population modeling is a good way to give researchers and governments the necessary tool that they need to make educated decisions that affect, hopefully, the future of the population. So today, we're going to look at population growth. We're going to look at three specific models of population growth: geometric growth, exponential growth, and logistic growth. And we're going to use learn how to use these mathematical population growth models to calculate the growth of population of various kinds of species in an ecosystem, and to look at what are the characteristics of these population growths. And also, we're going to be able to learn to describe the characteristics of a certain population, such as its growth or density or its distribution and even its minimum viable size. So population growth is measured as a change of population size over time. And this is typically reported as either a ratio or a percentage value. So in population change, you would take what is the change of a population. So for example, you might have to sum up all the births in that population, all the immigrations, whatever is added to that population, and subtract any deaths or emigrations, whatever has taken away from that population, and divide it by whatever was the initial population size that you were looking at. And in this case, if we want to report it as a percentage, multiply it by 100%, and that would give you an indication of what is the population change. And there's, as we said, three types of population growth models that we can consider: geometric, exponential, and logistic growth. We'll go through them one by one to make sure we all understand what they mean and how to use them. So in geometric growth, you have this type of growth in a case where there is an ideal environment, there's no limiting factors, and in this case, the population can grow in a geometric rate, or sometimes even an exponential rate. But in, for example, human-type populations, where individuals live and reproduce for many years, and our reproduction is distributed throughout the year, we get exponential growth. While in certain populations that may have a breeding season, where population growth is limited to those times, that is a geometric type of population growth. And population growth in those types of populations where there's a breeding season, that's when the population grows rapidly during the breeding season, and then during the remainder of the year, it declines. So during this breeding season where you have this population growth, the population grows at a certain fixed rate within a given time interval. And to calculate this geometric growth, you take the population size in 1 year and you compare it to the population size at the same time from a previous year. And scientists use this symbol lambda to represent geometric growth rate. And there is an equation here for calculating geometric growth rate, where lambda is the geometric growth rate or the fixed growth rate. Uppercase N is the population size in year. In t+1 year and the year t, respectively, t being the time or the year, for example, t could be the population size, n of t could be the population size in year 1, and so n at t2 would be the population size at year 2, or year 1, t plus 1, so that would make it year 2. And we can rearrange this equation so that we can determine the population and we can forecast it for a given time in the future. So we can rearrange this and figure out what is n at any given time t. So the population size at any specific time t, and n naught would be the initial population size. Lambda would be the growth rate, which we would have figured out by looking at how the population is growing over a certain time, and then the time t for whatever amount of time we want to forecast and look at that population in future. So these two equations are essentially the same, just rearranged somewhat. Let's look at an example for this type of geometric growth. So here in this example, looking at a population of polar bears that give birth each June. So each June, polar bears give birth, and the initial population is of 20 bears, giving birth to 6 cubs. And during the next 12 months, 3 bears die. If a population growth is geometric, as you would guess would be the case in this type of population where there's a breeding season, what will be the polar bear population in 2 years' time? And how about in 8 years' time? So first, to answer this type of question, we have to calculate the size of the population over the current year. What's the current year's population size? So we started out with 20 bears. They gave birth to 6 cubs, so plus 6, but then 3 unfortunately died, so minus 3. So our population size during this year of year 1 is 23. Now, to figure out how this polar bear's growth rate, what is this growth rate, figure out the lambda, we have to compare this population size, 23, with what was the original population size. What was the original population size, where we're told that the initial population or the original population was 20 bears. And then during the course of the next 12 months, 6 cubs were born and 3 died. So we are comparing 23 to 20. Okay. Oh, sorry, this thing has jumped. I will fix this. This looks a little weird. Maybe 0. Let's see if that starts to look a little more right here. There, that looks right. So n at t plus 1 over nt. Our nt is the initial population of 20. At t plus 1 in year 1, we have 23. So the growth rate, excuse me, In this case, it's reported as a ratio is 1.15. And we can use this now to calculate the population size in 2 years' time and then in 8 years' time. So we simply rearrange that equation and we substitute in that at n of 2, we have the population size times the population rate to the power of 2. And we see that in 2 years' time, we will have about 26 polar bears. Not 26.45, because you cannot have 0.45 of a bear, but the population, we will have 26 polar bears. And in 8 years' time, the same way. We calculate it using the same equation, and we can say that in 8 years' time, we will have 61 polar bears, not 61.18. You cannot have 0.18 of a bear. So 61 polar bears is what you're going to report here. So that was an example of geometric growth rate. Again, keeping in mind that this is the type of growth rate that happens when there's no limiting factors, but typically there is a breeding season and the growth happens at a fixed rate during this time and doesn't change much for the remainder of the year, or may even decline. The second type of population growth that we can look at is exponential growth. And this type also happens when the resources are plentiful, unrestricted, and so the population size will just increase exponentially. And as we said, this is typically what happens most of the time in human populations. And unlike geometric growth, which is intermittent, for example, breeding seasons, exponential growth occurs when in a population that grows continuously at a fixed rate in a fixed time interval. And in this case, the shape of the growth curve is exponential. It's this J-shaped curve, just goes up and up and up. And again, this is a case typically in a group like the human population, where their resources are plentiful, and the growth rate doesn't occur intermittently, rather it grows continuously at a fixed rate. We just keep on multiplying and having babies any time of the year, all year, whatever. There's no season or reason associated with it. In this case, the growth rate is measured as an intrinsic growth rate per capita. And you have the instantaneous growth rate for exponential growth rate calculated using this equation. dn over dt is equal to r times n, and dn over dt is the instantaneous growth rate of the population at any given time, at any given instant. R is the intrinsic growth rate per capita, and n is the population size. And then we can also use this formula to help us approximate a population's doubling time, which is TD, lowercase d to indicate doubling time. And this is a doubling time which occurs at an exponential rate. So these are two equations rather, that we can use for exponential growth. And if we were to look at an example, for example, we have bacteria growing on a petri dish. Again, this type of growth would be exponential because on a petri dish, it's quite a controlled environment. They have a nice, rich media in that petri dish to grow on. There are no real constraints or limiting factors. And in this case, you're told that the intrinsic growth rate, or R, is 0.2 per hour, and that the initial population is 1,000. So you started out with 1,000, and the growth rate is 0.02 per hour. So you're asked to calculate what is the initial instantaneous growth rate of that population. What is the time it would take for the population to double in size, and also to calculate the size of the population after each of 4 doubling times of the initial. So to answer this question, we write down what we know. We know that we have our intrinsic growth rate R is equal to 0.02 per hour. We have N, our initial population size is equal to 1,000. And we can use that relationship then to calculate the instantaneous growth rate, or dN over dt, of our at the initial time, our initial instantaneous growth rate. So this would be 20 per hour. We'd be growing at the rate of 20 per hour. So therefore, the instantaneous growth rate is 20 bacteria per hour, the initial instantaneous growth rate. Excuse me. The second part of the question, the time that it would take for the population to double in size. So we can use that equation to calculate the time for doubling, or T lowercase d here. So 0.69 divided by R, we know what is the value of R, 0.02 per hour. So the doubling time is every 34.5 hours. So now that we know what is the doubling time, doubles every 34.5 hours, we can answer the final part of the question that asks us to calculate the size of the population after each of 4 doubling times of the initial. So initially at time 0, we started out with a population size of 1,000, and this is just a simple T-chart you guys are familiar with. And the first doubling happens after 34.5 hours. So you double 1,000, you get 2,000. So after another 34.5 hours, you're at 69 hours. And now this population of 2,000 has doubled again. So we're at 4,000. After another 34.5 hours, we are at 103.5 hours, doubled again from 4,000 to 8,000. And finally, the fourth doubling time, after another 34.5 hours, we are at 138 hours, and our population doubles again from 8,000 to 16,000. So we've calculated the size of the population after each of 4 doubling times. First doubling time, second doubling time, third and fourth doubling time. And that's all. So that's how you can answer this type of question using these equations. Now, guys, on a test or an exam, you will be allowed a cheat sheet, of course, and you don't have to memorize these equations. Excuse me for moving that around. But what you do have to know is you have to know how to use them. So I might give you the equations, but you will have to know how to use them. Or better yet, if you're preparing a cheat sheet, write it on your cheat sheet and understand how you're going to use it. So then we're going to move on to our third type of population growth, and this is logistic growth. And logistic growth is actually the most common type of growth pattern that you find in nature, and it's affected by many different factors that can limit population growth, such as the availability of food and resources, such as light, water, space, shelter. And so initially what might happen is that the population might start to grow exponentially, but then growth may slow down. And when there's no net increase in the size of the population, in other words, when the number of births actually starts to equal to the number of deaths, so the population is no longer, there's no net change in the population, then at that point, the population has reached what we call the carrying capacity of the environment, where the environmental resources are such that it can only support a certain population size. That's the population's carrying capacity, the environment's carrying capacity. So this pattern of population change, this logistic type of growth, is represented with a mathematical model and an equation called the logistic growth equation, and where you have the instantaneous growth rate of the population can be calculated as follows. So again, dn over dt is the population growth rate at any given time. So at any instant, that's why it's called the instantaneous growth rate. R max is the maximum intrinsic growth rate. N, uppercase N, is the population size at a given time t. And K, uppercase K, is the carrying capacity of the environment. So in this case, you can look at this equation and you can observe what will happen if the carrying capacity K, sorry, this should be an uppercase K, approaches the population size N. If these two numbers become close, what happens then? Then it means that the population growth rate will approach 0, and so therefore no more growth occurs at that point. And this figure represents what you typically might see as the shape of a logistic growth curve. It's that typical, what we call a sigmoid shape, this S-shaped curve, where initially the growth rate accelerates until it reaches a point of maximum growth, and then the growth rate slows down. And where it starts to plateau off and level off, that's the carrying capacity of the environment, that number there. So if we look at, so this is just a very stylized, idealized shape of a growth curve. Maybe we might see something that might look something a little bit more like this. If we plot actual data, it might not exactly like this, but typically you see that there's 3 distinctive phases on a logistic type of growth curve. Initially, there is a lag phase. And during this phase, initially, the population is increasing very slowly. Then you hit that log or exponential phase, where during this period, you get very rapid population growth. And then you reach the stationary phase where the organism or the population is at or very close to its carrying capacity for that environment. And then sometimes it even follows by a death phase where it starts to die off again until it is able to reach a number that it can start growing again, where it once the environment is able to produce the amount of resources required for that number. So as the population approaches this stationary phase, as you get this growth and it's approaching this stationary phase, the resources that are available become limited, as you might imagine. The population can only grow so much off of a certain amount of limited resources. So the resources are very limited and the population can't continue to grow and reproduce rapidly like it was doing before. And so therefore, the number of births start to taper out and reduce, and the number of deaths start to increase. So you hit this stationary phase, and where this period of equilibrium, where you have as many births as many deaths. And that's why this is considered to be the carrying capacity of the environment for that organism. So if we look at an example for logistic growth, suppose you were given this type of a question where you say, a population is growing continuously, and the carrying capacity for the environment is 500 individuals, and the maximum growth rate is 0.25. And you're asked to determine the population growth based on a population size of 10, 50, 100, 200, 350, and 500. So we can use our equation that we know we can apply, and we can set up this table. We know the value of R max. We have been given the population size of N, which can be 10, 50, 100, 200, 350, or 500. And from this relationship and the value of R max, we can calculate dN over dt, the population growth. And if we do that, we will get these numbers. Okay. And that, guys, as I said, is a very short lesson, because I was hoping that we were going to get caught up with the rest of the presentations, but I can see those students who have not presented yet are still absent today. So do you guys have any questions? If nobody has any questions, this is going to be a very, very short lesson. You guys can use the rest of the time that you have left to work, for example, on your on your unit assignment, which, by the way, I have posted and shared with you. So yeah, any questions?
Miss, did you post a Dropbox for the assignment?
Oh, I have not. I need to do that. Gosh, I keep forgetting. I will do that. It's not quite so critical, because I can see all of your assignments during your presentation, which I have recorded and I can watch. But yes, I will set up the Dropbox. But yeah, not that critical. In a way, I already have a copy of it based on the recording and your presentation.
Okay, no problem.
Okay, thank you, Natalie.
No problem.